Okay, so number 23, chapter 2, number 23. Ready, Fred?
No, I'm ready.
Okay. So, same as number 22, essentially. We have an average atomic masses, and we have percentages. Okay? And I want to make sure you guys understand the premise of why we do what we do here, instead of remembering just some sort of kind of equation, having an understanding of what's going on. So we're going to approach this one with a little more explanation. So let's say there's a hat. There's a hat here, and in this hat I have 100 atoms of bromine. Okay? And we're going to draw those little atoms of bromine. Now, they come in different sizes. There's two different sizes. There's not just two atoms. There's 100 in there, but they come in different sizes. And so when I pull one out, I can identify its mass, whether it's, what do they say the masses are?
78.9183 or 80.9163.
That's right. Very good. Those are the masses. So they call those bromine 79 or bromine 81. So when I pull them out, I draw myself a little scale here, right? Have a little scale, and I pull it out, and it says whether it's the 79 or whether it's the 80. And then I write the mass, 78.981 or 183. Okay, there's that one. The next one, also 78.9183. The next one, it's 80.9163. Okay, so I keep pulling these out over and over and over, and I get a list of their different masses. And then if I want the average, how do I find the average?
You add all those up and divide by how many you have.
That's right. That's how I find the average. So if I were to do that in my calculator, if I were to add all these up, 78.9183 plus 78.9813 plus 80.9165, you can see it would take a long time if I were to add up a list of 100 numbers, right? That would just take a really long time, and then I would divide by 100. But that average would take a long time to put into the calculator. Can you think of an easier way? If I had a long list of 100 numbers here, right? Can you think of an easier way to add them all up and divide by how many there are?
Well, because you only have two masses, you can use a shortcut like just count up how many of one and how many of the other.
That's right. So here I have, for example, 1, 2, 3, 4 of the 78.9183. So I can write that 4 times that and simplify. Instead of having to write this in 4 times, I can just do 4 times that. And right now I just have 2 of these other ones. I can do 2 times the 80.9163. Right? I could add those together and divide by, how many would I divide by this time?
You have 6 there.
That's right, I have 6, so I divide by 6, and that would equal my average, right? So, that's essentially what I'm doing when I take the percentage, which is a description of how many there are for every 100, right? I'm taking the percentage and multiplying it by the mass. So when I say I have 50.69, that's out of 100. Out of the 100 balls that I pulled out, 50.69 of them are actually had a mass of 78.9183. Okay? So that is like adding up this 50.69 times. Okay?
Wait, how did you get 0.69 if there's only 100 balls?
Well, that's good. Way to recognize that, right? This was an example I chose of having 100 balls. But they didn't have 100 atoms in here when they actually counted, because apparently out of every 100, there was 50.69. So it looks like they counted 5,069 of these. And what's the other number? 4,931 of the other. Okay, so it looks like they had how many atoms in their hat that they were trying to pull out of?
Oh, 10,000.
That's right, the sum of those two, 10,000. But out of 100, it's this percentage, right? That's out of 100, it's 50.69. So 50.69 times whatever mass it was, right? Plus the other percentage, 49.31, times its mass, 80.9163. Okay? And then this divided by, this is a representation of 100, so that can give me the mass, the average mass that of the different atoms in that hat. I could also have done it like this. I could have said there was actually 5,069 atoms that had a mass of 78.9183 and 4,931 atoms that had a mass of 80.9163. And then I can divide that by what? What would I divide that by?
By 10,000.
That's right. So this is a representation of it having 10,000 atoms in the hat. And that would give me the same average, right? Give me the same average here as I would get over here. Okay? Good. So put that into your calculator. Another way that students like to do it to kind of save a little bit of time is to go not the average, sorry, not the percentage, but the fraction. The fraction.
What's the fraction?
It's like out of 1. If this was represented as one batch, what fraction of it would have a mass of this? And the answer is 0.5069. All right, so then I multiply that by 78.9183. And this one here would be 0 plus, again, 0.4931 times 80.9163. And I would only have to divide by 1. And so I could, put that step in there and make us feel good, but it's not going to change anything. So I would get the same average again here. So taking the fraction, multiplying it by those values, you don't have to divide by anything. All right, so let's see if we can get an answer here for ourselves. 0.5069 times 78.9183. I like to push enter to make sure there's no order of operation issues.
Is there going to be?
Well, there shouldn't be, but minimizing any possibility of making a mistake is always good. So this mass here plus that mass there should be my average mass of 79.90. Okay? That's what the average equals. Now, I can look and see how that compares to the actual average mass of bromine here. It is 79.90. So the batch that we had here was what you would expect to see in a large natural sample. Okay. Moving on. So hopefully you got a feel for how to do those ones. Here's another one. Variations in average atomic masses by observed elements obtained from different sources. Lithium provides an example of this. Isotopic composition from 2 different sources. A commercial source of lithium recycled from the military had that source. Calculate the average atomic mass values for these 2 sources. All right. I'm going to go 0.075. That's the percentage of the 6.01512. And what's the other one? 0.925. 7.016. All right. So 0.075 times 6.01512 0.925, 7.016, 6.94. All right. I'll let you guys work on the other one. Okay. Good stuff. I think the next one is probably very similar. Yep. And I think that if you're here to try to figure out how to do number 25, you should be able to follow the example of 23, 22, and 24 and get those answers just as well. This is a good practice, though. The answer should be in the back, and you can practice it and see if you can get it. Okay. Write the molecular and empirical formula for the following compounds.
What's the difference?
All right, the molecular and empirical formula. So there are chemical formulas. We've talked about a little bit of a few of them. H2O. In the news all the time you hear about carbon dioxide, and I think that we probably all, we don't know exactly where we learned it, but have an understanding of what that means, CO2. And these are chemical formulas, and they may be molecular formulas, meaning this is how the molecule actually resides in nature. Oxygen with 2 hydrogens, that's what water looks like. Carbon with 2 oxygens, that's what carbon dioxide looks like. Okay? Here's another compound that we utilize a lot in our lives. H2O2, that's hydrogen peroxide, right? There's just 2 oxygens with a hydrogen like this. It's not very stable. That's why you put it in your mouth to rinse out your mouth, to kind of like an antimicrobial solution. And it breaks down into oxygen and water, right? And creates a lot of white bubbles. Sometimes you can use it to get blood out of your clothes, stains that you might have, right? It's good at that as well. So hydrogen peroxide, this is what it looks like as a molecule. Therefore, this is its molecular formula. However, we could have a simpler representation of this, just HO. Same whole number ratio, right? So this is what we call the empirical formula. And while this one would be our molecular formula. Okay? So the empirical formula and the molecular formula have a relationship to each other, right? There's a number, a multiplier, and in this case it's 2. You multiply the empirical formula by 2 and you get the molecular formula. So when you look at carbon dioxide, because its molecular formula is already the simplest whole number ratio, it's the same as the empirical formula. So CO2 is the molecular formula, and it is also the empirical formula. All right, looking at the next one here, C2H2 it looks like, right? C2H2, what do you think? Is that the empirical or the molecular formula, Fred?
That must be the molecular formula.
That's right, we see what the compound looks like there. What would be the empirical formula?
Just the simplest, CH.
That's right, CH, the empirical formula here, the molecular formula here. What's the multiplier that goes to get from the empirical formula to the molecular formula?
It's 2 also.
That's right, you multiply by 2 and you can get from the empirical formula to the molecular formula. Good. What's the empirical formula here?
Looks like C2H4.
Okay, very good. So next problem here, C2H4, and the empirical formula?
CH2.
That's right, good. Empirical formula, CH2. Multiplier?
2.
Very good. How about this one?
This looks like 1 sulfur, 4 oxygen, and 2 hydrogens.
1 sulfur, 4 oxygens, and 2 hydrogens?
Yeah.
Very good. Very good. Now, we don't recognize this compound, so that's just as good as any, but generally, well, I shouldn't say that. This is a common compound, H2SO4. It's sulfuric acid, right? So I'm going to write it like that, H2SO4. How about, is that the molecular or the empirical formula?
That's the molecular formula.
That's the molecular formula.
Well, it's also the empirical formula.
How do you know?
Because it can't get any simpler. There's only one sulfur.
That's right. So it's the molecular formula and it's the empirical formula. Okay, good. Good stuff. All right, so the molecular and empirical formula for this compound here. What do you think, Fred?
It's got 4 carbons and 6 hydrogens.
I think there's more than 6, isn't there? C4.
Was it 8?
1, 2, 3, 4, 5, 6, 7, 8. Yeah, C4H8. So this is our molecular formula.
And our empirical formula is going to be half that.
C2H4.
Yeah, with a multiplier of 2.
Very good. To go from the empirical formula to the molecular formula, you have to multiply by 2. All right, here we go. What about this one?
4 carbons and 6 hydrogens.
All right, C4H6. All right, molecular formula. Empirical formula?
Hold on just a second. Did we do that last one right?
What's wrong with it? Oh, you're right. Look, C4H8, C2H4. We didn't quite get all the way down to the empirical formula.
No, it's CH2.
Very good, CH2. So what does that make this multiplier?
It's 4.
Very good. So CH2, and that's CH4H8. Okay. Good. All right. So C4H6 goes down to what?
C2H3.
C2H3, and that's the empirical formula. All right. Good stuff, Fred. Good job. What do we got here?
Looks like Si2Cl4H2.
Good. I would probably put the 2 H's first. H2, Si2, Cl4, something like that. You know, the actual order at this point in our experience doesn't matter. Okay, molecular formula. How about the empirical formula? Whoops. That's an F.
HSCl2.
HSiCl2.
Oh, yeah.
Okay, good. So, again, the multiplier is N times, or N equals what? Times 2?
Yeah.
Okay. All right. This one here.
H3PO4.
Oh, you said that like you know what that compound is.
Yeah, I don't know if I really do or not.
H3PO4.
That's the empirical formula too.
Yeah, that can't be simplified anyway. All right. Empirical formula for all these.
Well, that one can be divided by 2.
Yeah, so C4H5N2O.
That one can be divided by 11. Wow.
Yeah, good.
That one by 2.
Good.
That one by 2 also. No, by 6.
Yeah, by 6. Good.
And that one by, what was these? Is that 2?
Let's see, if we divided C6H8O6 by 2, we have C3H4O6, C3H4O3, right? Yeah, so 2.
Okay. Oh, and that's it.
Good. 32, same thing.
Divide that by 2.
That one divided by 2.
That one can't be divided because oxygen's 7.
Can't be divided because oxygen's 7.
That one by 2.
Okay.
That one by 2 also. And that one by 2.
Let's see, if we divide that by 2, it goes from C4H10 to C2H5, and that can't get any simpler, right? All right, so that's the molecular formula, and that's the empirical formula. Okay, good stuff. All right, number 36, we have a few more empirical formulas here. What's the molecular formula, Fred?
C2O2H4.
Okay, so I'll put the hydrogen first. That's typically what we, or not typically, but H4C2O2. Is that right?
Yeah, I think so.
Okay, so we have a molecular formula, and the empirical formula is what?
H2CO.
Very good, H2CO. Empirical formula, molecular formula. The next one,
C3, O2, H8.
good job. Okay, so C3, H8, O2, that's how you'd write it in organic chemistry. Carbon first, hydrogen, and then oxygen. If this is an acid, then you would write the hydrogen first. But anyway, all right. Can we, well, I don't think this is right. What's wrong, Fred?
What do you mean?
I think I see 4 carbons.
Oh yeah, 4 carbons.
See 4, H8O2. All right, so now we have an empirical formula of what?
Divide everything by 2. C2H4O.
C2H4O. Okay, good job. All right, so now we're going to identify these as elements, metals, or these elements as metals or nonmetals, and then further classify them as main group, representative elements, transition metals, or inner transition metals. Let's get our periodic table over here and remember these zones on the periodic table. You remember where the representative elements are?
Like the first 2 rows?
Columns, yeah, the first 2 columns.
Yeah, first 2 columns and the last 6 columns?
Very good. And the last 6 columns here. Those are our representative elements. Where are the transition metals?
Oh, those are the blue ones, right?
That's right. The transition metals are right here. Okay? And our inner transition metals,
I don't know.
that's these down here.
Okay.
And what else do we got? Main group, transition metals, and inner transition metals. Okay. So cobalt.
Cobalt is 27.
Very good.
It's a transition metal.
Very good. Blues are our transition. Europium,
Is europium 63?
63.
So that's a inner transition.
Very good. Iodine,
Oh, that's over 53. So that's representative.
good. Lithium,
Representative.
oxygen.
Representative.
Is oxygen a metal or a nonmetal?
Oxygen's a nonmetal.
Now, how do we separate the metals from the nonmetals?
That staircase.
That's right. The green staircase here separates the metals from the nonmetals with the exception of,
Hydrogen.
that's right, hydrogen. All right, cadmium.
That's a transition metal. It's number 48.
Very good. There it is. Let's see. Terbium. Terbium.
I don't know where terbium is.
It's probably down here, right? Oh, there it is. Terbium.
Okay, so it's an inner transition metal.
Good. Inner transition metal. Rhenium. Rhenium.
Oh, there it is, number 75.
Number 75. Rhenium. All right, so that's a what?
Transition metal.
Okay. Very good. All right, so use the periodic table to give the name and symbol for each of the following elements. All right, the halogen in the same period as the alkali metal with 11 protons. In the same period. So halogen, where are the halogens?
That's the second to the last on the end, right?
Very good. So these are our halogens right here. And it's looking for the halogen with 11 what? Protons?
11 protons?
The halogen in the same period as the alkali metal with 11 protons.
Oh, the alkali metal. Alkali metal is the first row, right?
These are our alkali metals. Here's the alkali metal with 11 protons. So they're talking about chlorine, aren't they? The halogen in the same period is going across here as the alkali metal with 11. Okay, that's fun. The alkaline earth metal. What column is that?
Second column.
Alkaline earth metal in the same period with the neutral noble gas with 18. So 18 is argon, so they're talking about the alkali earth metal, so that's magnesium. C. You do this one, Fred.
The noble gas in the same row as an isotope with 30 neutrons and 25 protons. 25 protons, that's the mass of 20, that's 25, let's see, which one is that? That's manganese, 25.
Very good, 25 protons, manganese.
So we're looking for the noble gas in that column, or that row, and that's krypton.
Okay, good. Noble gas in the same period as gold. gold. There it is, xenon. All right, use the periodic table. Predict whether the following chlorides are ionic or covalent. All right. How do we distinguish whether a compound is ionic or covalent, Fred?
Ionic compounds contain metals.
Very good. Ionic compounds strictly are, the definition is they're made of ions. But if they contain metals, then they're going to be containing ions because ions form metals. Metals form ions when they form compounds. Okay. So let's look. SiCl4.
Si, that's a metalloid.
All right. So that one would not be a ionic compound. It would be a covalent compound. PCl3.
Same thing, covalent compound or molecular.
Very good. Ionic or covalent. Molecular, also another way of saying covalent. All right. CaCl2.
Calcium's a metal.
Very good. There's calcium over here. It's a metal, so that's an ionic compound. Huh?
Yeah.
CSCl.
Cesium's a metal, so that's a ionic compound.
Copper.
That's a metal, so that's an ionic compound. Chromium is too.
Very good. So we got ionic, 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 ionic. And then our molecular ones are these two right there. Okay, good stuff. Here, ionic or covalent? What do you think, Fred? Ionic or covalent for NH3?
That's covalent because nitrogen and fluorine are both nonmetals.
Very good. Nitrogen and fluorine, right of the staircase, nonmetals, covalent compound. How about BaO?
Barium is a metal.
Where's it at?
It's element 56.
Okay, metal. So ionic compound. How about this one?
That one's kind of tricky because it has no metals, but it is ionic because it's made of ions.
Very good. So the ammonium ion is pretty much the only one that's going to be forming ionic compounds. So that's another way of seeing or remembering ionic compounds if it contains the ammonium ion. Do you have a list of your polyatomic ions?
Not on me, no.
Well, you should print out a list of, on your periodic table, on the back is that list of polyatomic ions. And remember that the deal is anytime we come across an ionic compound, or a polyatomic ion, sorry, we bring out our polyatomic ion list and we find it on the list, okay? So here it is, it's the ammonium ion right there on the list, okay? +1 charge, all right? Now, the CO3, we have to look for it. It's also a polyatomic ion. Do you see it?
Oh, there it is.
Right here. So it has a -2 charge. And notice how there's 2 ammonium, right? Right, that number right there indicates that there's 2 ammonium, the 2 there, and there's 1 carbonate. And there's 2 ammonium because each ammonium ion, NH4, has only a positive charge, whereas each carbonate ion has a -2 charge, right, 2- charge. So you need 2 of these because we need to have those charges balanced, and there's just 2 negatives, and now we have 2 positives. So NH4, 2, CO3, ammonium carbonate, an ionic compound. Okay, how about the next one?
Strontium is a metal, so it's ionic.
All right, strontium is a metal. We'll bring our periodic table back up here. Strontium's a metal, so it's an ionic compound.
Is that IBr or LBr?
That's IBr.
So they're both non-metals, so that's covalent or molecular.
Very good, covalent or molecular. Sodium, is that a metal or a non-metal?
That's a metal.
So that makes it what?
Ionic.
Okay. Ionic, let's see. If it's ionic, write the symbols for the ions involved. So same thing, ionic or covalent. It's a good game, right?
It's not bad.
And then we're going to identify the ions that are involved if it is ionic. Okay? So let's take a look here. Is this one ionic or covalent?
Potassium. That's number 819. It's a metal, so this is ionic compound.
Very good. So now we know that we have this compound, potassium, ClO4. Oh, there's a polyatomic ion. What do we do when we see a polyatomic ion?
Get out the periodic polyatomic ion chart.
All right, let's find it on here. ClO4, there it is, the perchlorate. Potassium ion and perchlorate ion. So this is potassium perchlorate. All right, that's the name of that compound, potassium perchlorate. We see that there's one potassium ion and one perchlorate ion. I had the polyatomic ion chart. It said that that's what the perchlorate ion looks like. I know that the potassium ion looks like that because, remember how we know that, Fred?
No, I can't remember.
We know that because potassium has 19 electrons and protons as a neutral atom. Here it is, neutral atom, 19 protons, 19 electrons. If it's going to form an ionic compound, it's going to want to attain a noble gas electron configuration. And so to do that, it has to have one of these numbers. 18 is the closest. So it's going to lose one electron, and when it loses one electron, it's going to have one fewer electrons than it has protons, and that's going to result in one positive charge there. All right, so this is what they were looking for, the symbols for the two ions that are involved in this compound, ionic compound. All right, next one.
Mg, that's magnesium.
And then the other thing, what's that?
I don't know.
So let's look it up here on the periodic table, or sorry, the polyatomic ion table. See if you can find it.
I'm not seeing that. I don't think it's on there.
Okay, here is the acetate ion, CH3COO minus.
And that's a little bit different.
It is written a little bit different, and this is probably should not be written that way. So I'm going to fix that and write in here also C2H3O2. So I've rewritten the acetate ion as the C2H3O2 minus. So anybody printing up a polyatomic ion chart from this point going forward will have both options there. Okay? You see it written like this mostly in organic chemistry. In inorganic chemistry, which is what we're studying right now, it's written like this usually. Okay, good. So this is the acetate ion. Magnesium acetate is the name of the compound. And what are our ions?
We have the magnesium ion and the acetate ion.
All right, the acetate ion is easy. Because we have this chart here, C2H3O2 minus. But what's the charge on the magnesium ion?
Well, the acetate's minus, so the magnesium must be plus.
It's not that easy. Notice here how many acetate ions there are for every magnesium.
Oh, there's two.
That's right, there's two of these acetate ions for every magnesium. Does that help you?
Maybe, I don't know.
Well, we know that because this is the ratio, that the charge, the sum of the minus charges has to equal the sum of the positive charges. So that helps me know right there that this must be a +2 charge, right? Another way we could do that is look at magnesium and see that it's a representative element, therefore its location. All of the alkaline earth are going to have a +2 charge. Another way of thinking about it is if it has 12 protons and electrons as a neutral atom, it's going to want to attain a noble gas electron configuration, and that's going to be 10. So it's going to want to lose 2 electrons and have a +2 charge. Okay, good. H2S.
H2S, is that a molecular compound?
It is a molecular compound. Now let's see. State whether it's ionic or covalent. It's a molecular compound, so H2S is a covalent compound.
Okay, so that's it. That's all we have to do for that, right?
That's right. All right, this next one, ionic or covalent?
Ag, is that gold?
It's not gold, but it is silver.
Oh, silver, yeah.
Okay, so silver, what are you going to call that compound, you know?
Well, there's a silver and a sulfur.
Very good. So that's a good place to start. If we write down Ag and we write down S. Now, Ag is not a representative element, so its location on the periodic table doesn't lead us to know exactly what its ionic compound, or what it would form when it makes, what kind of ion it would form when it's in an ionic compound. Sulfur, on the other hand, is a representative element, and we can tell based on its location that it's going to do what in ionic compounds?
It has 16 electrons,
16 as a neutral atom.
and it's going to want to get 18.
That's right. It's going to want to get 18 to have a noble gas electron configuration. So it's going to gain 2 electrons. So that's a 2 minus charge there. How about silver? Where do we say silver? What is it going to want to do?
I don't know. How can we tell?
Well, again, we can't tell from its location here, but we can tell by looking at this compound and seeing the number of sulfurs relative to silvers. There are 2 silvers for every sulfur. You see how there's Ag2S, right? Okay. So if sulfur has a 2 minus and there's 2 silvers, that means that each silver has to have a +1. All right. And again, we knew that because these 2 have to balance off that charge there. All right. Next, E, N2Cl4.
That's a molecular compound, both nonmetals.
Very good. Next one.
Cobalt, that's a metal.
Very good. It's a metal here. All right. What's the other ion?
That's a polyatomic ion. We need to look at the sheet.
Very good. Let's bring out the sheet. Where is the sheet? There it is. Tell me when you see it.
I think it's up higher. Still don't see it. Oh, there it is.
All right. So nitrate ion, right? NO3. Is that right?
NO3. Oh, look, there's the nitrate. Yeah, it's NO3.
Okay, good. Nitrate ion. So the nitrate ion has a -1 charge. How many nitrates ions are there in this compound?
There's 2.
All right, so there's 2 of these NO3 minus. I know this is what the polyatomic ion looks like because I looked at here on the periodic table. I know it's the nitrate ion. So how many cobalts are there?
Just 1.
1 cobalt. So what must be that charge on that cobalt?
Has to be a +2.
That's right. It has to be a 2+ because there are 2 nitrates and 1 cobalt. All right, 49. For each of the following pairs of ions, write the resulting formula of the compound that will form. All right, pretty straightforward, right?
Well, we've been kind of doing that already.
That's right. So here we can see that when we combine the calcium ion, this is A, 49A, and the, what do you call that thing?
Is that the sulfide ion or the sulfate? Sulfite? I can't remember.
All right. So here we have polyatomic ion showing us that sulfate is there. And here's the sulfite. All right. What is that? And remember, when it's what we call a monatomic ion, right? Non-metal, monatomic anion, we just call it by its name and we give it the "ide" ending, sulfide, sulfide. So this compound is going to be called calcium sulfide. And this combination, there's a couple ways to do this. There's this little crisscross rule where you can say, okay, so it must be C2S2, but then you have to simplify this, so it's CAS. All right, the other way to do it is just to say, okay, this has a +2 charge, this has a -2 charge, so I'm going to need 1 of these for every one of those. Okay, calcium sulfide. All right, next one. What are those 2 ions?
Is that the ammonium ion?
Very good. The ammonium ion.
And I need the polyatomic ion chart for that one.
All right.
Oh, there it is. It's a sulfate ion.
Very good. Down here, the sulfate ion. So the ammonium ion, which we went over not too long ago, and then the sulfate ion. Okay. So what's the charge on the ammonium ion?
It's just +1, right?
Yeah, there it is. The ammonium ion's a +1. And the sulfate ion?
It's a -2.
All right, SO4 2-. Okay. So how are they going to come together?
You're going to need 2 ammonium ions.
2 of these ammonium ions. And the way we indicate that is we say NH4, 2 of those coming together with 1 of these, SO4. Okay, good. Ammonium sulfate. Next is letter C. We have aluminum ion and bromide ion. Okay. Aluminum, bring up our periodic table here. It's a metal, so we don't call it the aluminide ion, right? It's just the aluminum. But bromine is a nonmetal, so it becomes the bromide ion. Okay. So we have aluminum, Al plus 3 and Br minus 1. What does that mean that we need?
So we need 3 of the bromide ions and 1 aluminum.
Very good. We're going to need Al Br 3, like that. And there's the crisscross rule works really well there in that scenario. Or you can just see that we have a 3 plus and a minus 1. Okay, the next one.
Is that the sodium ion?
Very good. Sodium ion.
And then I don't know the other one.
All right, so we bring up our periodic table here. Sorry, polyatomic ion table. Let's see, do we have any of those ones on here?
Oh, there it is, the hydrogen phosphate.
Hydrogen phosphate has a 2 minus charge. All right, so how we're going to have to combine the sodium ion and the hydrogen phosphate ion to get a compound.
You're going to need 2 sodiums.
That's right. I'm going to need 2 of the sodiums for every HPO4 2 minus. Okay, very good. So the resulting compound is going to be Na2 HPO4. All right, the next one.
Let's see, is that the magnesium ion?
That's the magnesium ion. And what's the other one?
I'm looking at the polyatomic. Oh, it's the phosphate ion.
Very good. Right there we got the phosphate ion, right? All right, so magnesium and the phosphate. All right, the crisscross rule works really well here. Magnesium 3, PO4 2. I have to make sure I put that in parentheses though, because this I'm having 2 of this whole thing. So I needed 3 of these magnesium 2 pluses, and I needed 2 of these phosphate 3 minuses, minus 6 and a plus 6, 2 plus 3. Okay, good. Each of the following pairs of ions, write the formula for the compound they'll form together. Okay, so more of the same. All right, so we got potassium ions and oxygen ions.
I'm good at this now. It's K2O.
Very good, K2O. Right, because 1 potassium ion and 1 oxygen ion, oxide ion, and they come together so that I need 2 of these, 2 pluses for that 2 minus.
The next one, ammonium and then phosphate. Ammonium phosphate.
Very good. How many ammoniums?
You're going to need 3.
Very good. NH4, 3 of those for every PO4 3 minus, right? And again, there was the PO4 3 minus, and we had NH4 plus, and we saw that for these to balance, I was going to need more of the positively charged ions. So I had 3 of them for every one of those, and that's what that's representing right there. No charge there.
Next one's C.
All right, aluminum and oxygen. What do we do?
Aluminum is a plus 3 charge.
That's right.
Oxygen's a minus 2.
Yep.
So it's going to be Al2O3.
Very good. Al2O3. Because plus 3, 2 minus. That's an easy way. Whoops. That little crisscross rule is an easy way to kind of see it. But Al3 plus, Al3 plus, 2 of those gives me plus 6. O2 minus, O2 minus, 3 of those gives me plus 6. Okay, good. And that compound's name, do you have any idea?
Aluminum oxide.
That's right, good. Okay, the next one.
Na2CO3.
That's right, Na2CO3. So we have 2 sodiums because each CO3, what is the CO3?
Oh, does it say down there? I can't see. Oh, there it is, the carbonate ion.
That's right, carbonate, CO3 2 minus. So each carbonate has a minus 2, so you're going to need 2 positively charged sodiums. So it's going to be Na2CO3. That's the resulting compound. All right. The next one.
Is that barium?
Yeah. Periodic table right here. Barium. There it is. 56. Barium.
And then phosphate?
Is that the phosphate?
Yeah, that's the only one with phosphorus.
Let's see. Do we have, see, phosphate is the only one on this list. There's the dihydrogen phosphate and the hydrogen phosphate. There's also, it's not on this list, and this is an important lesson, there's the phosphite, which is PO3, 3 minus, all right? So there are lots of other polyatomic ions, hundreds of other polyatomic ions that aren't on this list. So, we have to be ready to be able to kind of work our way around polyatomic ions that we're not familiar with also. But this is the phosphate ion here. So what's our chemical formula going to be?
Va3PO42.
Va3PO42, like that.
Well, you need the parentheses.
Parentheses around here to make sure that we say that we have 2 phosphates.
Yeah.
Okay. Name the following compounds.
Okay, here we go.
So, do you remember much about naming, or do you know much about naming?
Well, we talked about it in class.
All right, what do you remember?
Name of the metal, or the first ion, or first compound. Well, it's different for molecular and ionic, right?
That's right. It's different from molecular and ionic. And in here, number 51 here, we have some ionic, but 1 molecular, right? So for ionic compounds, the way that we name them is we name the 2 ions, right? And if the ionic compound contains a metal that can have multiple charge states, like the transition metals here, or the intertransition metals, or even some of these metals down here. If it contains a metal other than these 2 here and really aluminum, I mean, there's some exceptions, but in general, we need a way to identify what the resulting charge is on that compound, okay? On that metal in that compound, all right? And the way that we do that is by just saying that charge. If the metal is in this box here, then you don't have to, because we know we don't have to distinguish what the charge is. We know that it's a +1 over here and a +2 over here. So for this first one, CS is cesium, Cl is chloride. It's just cesium chloride. Second one, Ba is barium, and that's oxygen. Barium, again, is our representative element, it's just barium oxide. All right, the third one here, potassium and sulfur, potassium sulfide. All right, Be, beryllium, Cl, chloride, beryllium chloride. Now HBr, what's different about HBr?
It's not an ionic compound.
Okay, good. How did you know?
Hydrogen's a nonmetal and Br is also.
So we name it differently. We use our prefixes to name it. Now, it's not too different if we look at this after we look at the prefixes, because let's talk about our prefixes really quick. Our prefix is for identifying the number of atoms in molecular compounds. It's just mono, di, tri, a monocycle, what do you call those? One-wheel unicycle. Mono, what's one? Mono, I don't know. For some reason that reminds me of one though. Di, that's always 2. Tri, that's always 3. Those are easy. 4 is a little bit tricky though. Let's skip 4 for a second. 1, 2, 3, 4, 5. 5 is, you know what you call a 5-sided figure?
Pentagon?
Very good. So pent. 6, 6-sided figure.
Hexagon?
Hex. 1, 2, 3, 4, 5, 6. All right. 7-sided. Do you know what a 7-sided figure is?
No.
8-sided figure, or just 8 in general?
Is that octopus? Like oct?
Yes, that's right. Oct. 9,
No, I don't know 9.
10.
Is it like decade? Dec?
That's right. Decade, or decimal is another way to remember it. Okay. So we need a way to remember 4, 7, and 9, it looks like. Okay, so here's the way that I remember 4. Okay. There is a game out there that you've probably got hooked into playing at least a couple times. Probably got over it pretty fast. But it's called Tetris. Have you ever heard of Tetris?
I guess so. I'm not sure.
Let me bring it up here.
Oh yeah, I know that game.
Free online game. Play Tetris. Here we go. We're playing Tetris. Probably have to watch an advertisement. Bring it on. I'm ready to play. Tetris, Tetris, Tetris. Continue. Oh no, is that a joke? Yeah, it's going to trick me. Okay, close that. Get out of the way. All right, here we go. Let's play some Tetris. Yeah, baby. Okay, so here's how you do it. Tetris, it lowers blocks of 4. See that? There's a 4 block there. And I push that down there. When I get it down, I get another block of 4. And I line up these blocks of 4. See, there's another 4. Here's another 4. I can oops. Somehow I can, there it is. I push that button to flip it. All right. So I keep doing this until I get a line all the way across. Oh, so close. I did it. All right. So, Tetris. They call it Tetris because it's dealing with blocks of 4. Oh, look at that. I didn't know I could do it with my mouse, too. That's nice. All right. So why don't you guys play Tetris for a little bit so that you'll remember that 4 is tetra. Okay. 7. 7. How are we going to remember 7? Well, the months are January, February, March, April, May, June, July, August, AUG, September, October, November, December, right? October is 8, November is 9, December is 10, September is 7. So look at that. We have built in the numbers for the months. I always have trouble remembering which month is which number each month is, right? Well, here now we don't have to ever forget. See, December, Dec, 10. Nov is the prefix for 9, and that one we'll put in there. It's actually non for 9. Hept is actually the prefix for 7. Hept, Nov or non, and Dec, and Oct we already had. Okay, so there's where we get those.
I was born in December, but it's not the 10th month.
December? Oh, yes, you're right. Sorry about that. December is not the 10th month, is it? It's the what?
It's the 12th month.
Okay, so these names, September, October, November, December, stem from these numbers, 7, 8, 9, 10. And back in the day when we only had 10 months, where we constantly had to reset the calendar because the seasons would get off, that's where these names originate from. Julius and Augustus Caesar, the Romans, put in a couple more months for us to adjust so they wouldn't have to reset the calendar as often. And so that's where we got these 2 months, or these months all pushed back to numbers, right? So this is actually the 9th, 10th, 11th, and 12th, but that's where the stems of these words come from, 7, 8, 9, and 10. So sept is how I remember hept, and November, non, and I could use October and December that way as well, but I don't have any trouble remembering 8 for octopus and D for decade or December. All right, lots of information.
Yeah, that was a little much.
But these are the prefixes you need to use when you name the molecular or covalent compounds. Okay? So we have HBr, that's a molecular compound. So we could call it monohydrogen monobromide, all right? But oftentimes you omit the mono unless you have a really good reason for distinguishing it from other compounds. For example, CO2 and CO, we always call that one carbon monoxide because there's carbon dioxide, which is very popular, and we need to make sure we distinguish it. We can't just call one carbon oxide and the other carbon dioxide because we're always talking about carbon dioxide, so we might confuse people, right? But HBr, there's only one way that they can come together, and so we'll just be calling it hydrogen bromide, right? We could call it hydrogen monobromide, but because bromine can't come together with hydrogen in any other way, right? It wants to, well, we have to talk about molecular compounds and why they do what they do in the future. But for now, yeah, you can call it hydrogen bromide is the correct answer there. All right, ALF. What do you think about that compound?
Well, that's an ionic.
Very good, ionic compound. We can go back to our periodic table, see that it's aluminum, metal, non-metal.
So it's just aluminum fluoride.
Very good, aluminum fluoride. Excellent. So more naming opportunities. 52A, what do you think?
Just sodium fluoride.
Very good. I'll bring the periodic table up a little closer so we can see. Sodium and fluoride, both representative elements. No clarification needed in terms of what kind of charge they would form.
Rubidium oxide.
Very good. Rubidium and oxygen, both representative elements.
BCl3s. Boron, metal?
It's not a metal. It's a metalloid, right? So it not necessarily considered an ionic compound. It's going to form a molecular compound with chlorine.
So what do we do?
Remember, for the molecular compounds, if there's more than one element, we use these prefixes.
So monoboron trichloride?
Okay, good. Very good. We don't have to say monoboron. We can just say boron trichloride. Okay? And notice how when we did that, we didn't say boron trichlorine, right? We ended it in chloride. So the last suffix of the second element ends in ide. Okay, covalent compound. So we use the prefixes to help us know how many of different elements there are.
H2SE, that's is that a molecular compound?
It is a molecular compound. It's a molecular compound. All right. H2SE.
Dihydrogen selenide?
Very good. Selenium down here, right? Is that how you knew that?
Yeah, I was looking at that.
And then hydrogen, non-metals, coming together to form a compound. We use our prefixes, right? Dihydrogen selenide. All right, selenium goes to selenide. Let's write that one down for us. Now, okay? Now, we are also getting into naming acids, right? Acids. And HBr and H2SE are acids. Elements, are molecular compounds, covalent compounds that start with hydrogen or have hydrogens are usually acids, considered acids. All right. Now, they don't actually become their acids until they're mixed with water. And so it's okay to call this hydrogen bromide and dihydrogen selenide as it's been displayed to you. But you want to make sure you remember that once it is placed in water, then it becomes an acid. and we have to follow that in acid naming rules. Okay. All right. So hydrobromic and hydroselenic follow this binary acids hydroblankic model when they're placed in water. When they're not in water, we can call them hydrogen bromide and dihydrogen selenide. All right, next, P4O6.
Is that an acid?
No. How can you tell it's not an acid?
I don't know.
No hydrogens, right? Acids are about compounds that contain hydrogens. When you put them in water, those hydrogens will come off as hydrogen ions. Hydrogen ions. So we'll talk more about that in the future. P4O6, that's phosphorus and oxygen coming together to form a what? Molecular or ionic compound?
Molecular.
Very good. Nonmetals, phosphorus and oxygen.
4. Let me see if I remember the prefixes.
Okay, you think about the prefixes. I'll have them right here ready for when you're ready.
4 was tetra. Tetraphosphorus. 6 is, I can't remember 6.
You got to remember the six-sided figure.
Oh, a hexagon. Tetraphosphorus hexaoxide.
Very good. Hexaoxide, right? You know, you caught yourself. It's not oxygen, it's oxide. Okay, good. So tetraphosphorus hexaoxide. Excellent. All right, the last one there.
Iodine and chlorine. So iodine trichloride. Iodine trichloride.
Very good. Iodine, first one, and the end is going to end in CHLORIDE, chloride. And we put the tri in there to say that we have 3 chlorines. We name it this way because it's what? A molecular or ionic compound?
Molecular.
That's right. It has an I and a chloride. Those are nonmetals. Okay, good. Naming's, or now we're going to write the formula for these compounds.
Rubidium bromide. Where's rubidium?
Rubidium, right down here, right?
Oh, RB, and bromide is BR.
Okay, so rubidium and bromide. Okay, now before we can combine them together, we need to have an understanding of the kinds of compound this is. Is this an ionic compound or molecular compound?
It's an ionic compound.
All right, and now we have to think about what kind of ions these two elements are going to form and then bring them together to form that ionic compound.
Well, rubidium forms a +1 charge.
Okay, rubidium is here. It's first column, 37, right? Going to want to have 36 electrons to attain a noble gas electron configuration. So it's going to form a +1 charge.
And bromine's a -1.
Very good. Bromine, same thing we've talked about before. It's here, wants 1 electron, so it's going to have a -1 charge. Now when these come together, what are they going to form?
RBBR.
All right, 1 rubidium for 1 bromide. All right, rubidium bromide. Very good.
Magnesium and selenide, huh?
Yeah, selenium, here it is, 34, and magnesium over here.
Selenide's a -2 and magnesium's a +2.
All right, magnesium is a +2 because of its location. Selenide's a -2. So it's just going to be bringing these two together. Whoops. We like to write the 2 first when we're talking about charges, all right, instead of oxidation state, which is very similar, but we'll get to that in the future. But these come together. What's the resulting compound?
MgSe.
Very good. MgSe, magnesium selenide. All right, sodium oxide.
Sodium has a +1. I know that. I remember that.
Sodium's a +1.
Oxygen's a -2.
2 minus.
So 2 sodiums and 1 oxygen.
And a 2O. Very good.
Calcium chloride, Ca is a +2.
Because of its location on the periodic table here, right?
Chloride is a -1 because of its location. So CaCl2.
Very good. Calcium chloride.
Hydrogen fluoride. Hydrogen fluoride. That's just HF, right?
Very good. Hydrogen fluoride. So we know that we have hydrogen, which is a nonmetal, fluorine, which is a nonmetal. They are I mean, by the name here, hydrogen fluoride, it's not indicating more of any of the others, no di, tris, or anything like that. So HF is our hydrogen fluoride. Hydrogen fluoride is also an acid. So when placed into water, would you know how to name that?
The acid?
Yeah,
I don't remember.
that's a binary acid, right? Let me see if I have those rules that I wrote down here. Binary acid. Therefore, it's going to follow. What are those rules that I had written down? Yeah. Oh, there they are, right there. Binary acid follows this pattern of hydroblankic acid. So
Hydrofluoric?
that's right, hydrofluoric. HF, hydrofluoric acid. These are just binary acids, so don't get confused with that. Okay, very good. So hydrogen fluoride is HF, that's E. All right, F.
Gallium phosphide.
All right, here's gallium and phosphide. Phosphide. What's the phosphide ion?
Is that a polyatomic ion?
Well, we can check it out, right? We can bring our polyatomic ion here and look through these names, see if we can find any phosphides or anything like that.
I just see phosphate and hydrogen phosphate and dihydrogen phosphate.
Yeah, no phosphide. So phosphide sounds like chloride, right? So it's just phosphide, phosphorus forming an ion. Okay? What kind of an ion is phosphorus going to want to form? What kind of a monatomic ion?
-3?
Very good. It wants to have 3 more electrons. And so its phosphorus is going to be forming a 3- phosphide ion.
Gallium, is that a +3?
Here's gallium. All right. So, yeah, gallium is kind of an interesting one. It can form multiple charge states. However, I think that what they're trying to get at here is that it forms a +3. It can also form a +1. We haven't talked about why that's the case yet. But if I wanted to let people know, so here we're looking at, again, our transition metals and any metals down here have the possibility of forming multiple charge states. I mean, either it could be a +1, +2, +3, +4, +5, or there's a variety of options for it. And so for gallium, if I want to help somebody know what the charge is on the gallium, and in this case, I'm going to say it's a gallium +3+, right? Then I'm going to call this gallium 3 phosphide. They didn't indicate to us whether it was gallium 3 phosphide or gallium 1 phosphide. If it's gallium 3 phosphide, then it's GAP. If it's gallium 1 phosphide, it's going to be, right, a +1, and I'm going to need 3 of those for every phosphide. So then it's going to be GA3P. Okay? So gallium phosphide, this is gallium 1 phosphide, this is gallium 3 phosphide. And it doesn't indicate which one you're talking about there. So I think that this is what they're referring to. All right, aluminum bromide. Aluminum bromide.
Aluminum is +3, right? And bromide's a -1, so AlBr3.
Good, that was good. Br3. Bromide, -1, -1, -1, and aluminum, +3. We knew all this because of this location. Aluminum is a +3 ion, forms +3 ion, bromide a -1. And so we need 3 of these for every one of those so that the charges balance out.
Ammonium sulfate. Those are all polyatomic ions.
Good, you're getting to know the polyatomic ions, huh?
Yeah, a little bit.
All right, so let's bring out our polyatomic ion chart. Remember, we always have to bring out our polyatomic ion chart. We took the pledge, promised to always look at the polyatomic ion chart when we look at when we see polyatomic ions. All right, so we're looking at H, ammonium. You see the ammonium?
It's right there.
There it is, ammonium. And then ammonium what? Ammonium sulfate, H, ammonium sulfate. Sulfate, do you see the sulfate?
There it is.
All right, so the ammonium ion was this NH4 plus, and the sulfate, SO4 2 minus. Okay, so how are those going to come together?
I need 2 ammonium ions.
You need 2 ammonium ions for every 1 sulfate. So NH4, 2, SO4. There's our ammonium sulfate. All right, continuing on to 54, lithium carbonate.
Lithium, that's not a polyatomic ion.
No, that's just a, whoops, where did my stuff go? That is just a element. There's lithium.
+1 charge.
All right, so lithium forms a +1 charge. And carbonate.
That's a polyatomic ion.
Carbonate's a polyatomic ion. Let's see if we can find it. There it is right there, CO3 2 minus. CO3 2 minus. What are we going to have to do here?
You need 2 lithiums,
How did you know?
because I need 2 positives if I have 2 negatives.
Very good. So lithium carbonate is going to have that chemical formula. Good.
Sodium perchlorate.
All right.
Na is sodium, and perchlorate is ClO4, is that right?
Let's see if you're right.
Yeah, I'm right, there it is.
Very good. Perchlorate, ClO4. You didn't say the minus sign, though.
Oh, you're right, I didn't.
Is that minus sign important?
Yes, it is.
So even though you know the chemical formula, you need to make sure that you look at here to remember the the charge on the polyatomic ion.
It's just a 1-to-1.
That's right, 1 sodium for every ClO4 minus. So that is the resulting chemical formula for sodium perchlorate.
Next one is barium hydroxide.
Barium hydroxide. All right, barium is Ba, right? Do you remember what the hydroxide ion is?
No, what's that?
That is a polyatomic ion.
Oh, there it is right there, -1.
Very good. OH minus 1. What's the charge on barium?
Oh, I can't remember.
All right, so let's bring up the periodic table here. Whoops. Periodic table. See barium?
Yeah, there it is, +2 charge.
Good. Its location on the periodic table tells us it's a +2 charge. Hydroxide ion is -1. All right, so what's our chemical formula going to be?
BaOH2.
Like this?
Yeah.
Nothing wrong with that?
No, that's okay.
All right. We have to make sure we have the parentheses around the hydroxide ion, because this 2, we want to make sure we show that it's this and not oxygen with 2 hydrogens, right?
Oh, okay.
All right, barium hydroxide. All right, where are we at now? D.
Ammonium carbonate. Didn't we just do that one?
Did we do ammonium carbonate? I think we did it a while back, but I don't think we just did that one. I think we did ammonium perchlorate or something else. But ammonium carbonate.
Ammonium, I remember, NH4 plus.
NH4 plus, but if you don't remember, you have to look here on the periodic, the polyatomic ion chart, and even if you remember, I prefer that you look there for a while till you get used to it. So here's the ammonium ion, NH4 plus.
And carbonate?
Yeah, carbonate is CO3 2 minus. Do you see it?
No, I don't see it. Oh, there it is.
CO3 2 minus. Okay, CO3 2 minus.
So there's need to be 2 ammoniums?
That's right, 2 ammoniums, NH4 plus. NH4, there's 2 of them, and then CO3, like that.
Ammonium carbonate.
Very good.
Oh, sulfuric acid. Oh, look, it's an acid.
All right, sulfuric acid. What's the chemical formula for sulfuric acid?
Sulfuric. I forgot how to name acids.
All right. So when we want to name acids, we have to determine whether it's a binary acid or an acid that contains a polyatomic ion. All right. So sulfuric acid, is that a binary acid or an acid that contains a polyatomic ion?
Now, I don't know. How can you tell?
Binary acids, remember we just had that. I'll rewrite it again because it's good to ingrain into our minds. But binary acids, yeah, I'll rewrite it. Now, what does binary mean again?
Just contains two um, elements.
That's right, two elements, binary acids. So with some examples of binary acids, HCl, H2S, right? Just two different kinds of elements, binary acids. And their model for naming, being named, is the hydroblankic acid.
Like hydrochloric acid.
That's a good model for us to remember because, or a good example, because everybody kind of knows that HCl is hydrochloric acid. We pick it up along the way somewhere. So hydrochloric acid. All right. So if it starts with hydro, that's how you know. Whoops. I wanted to put in here just the blank. Hydroblankic. That's for chlorohydrosulfuric acid. If it starts with hydro, that means it's a binary acid. If it doesn't start with hydro, and does sulfuric acid start with hydro?
No, I guess not.
Sulfuric acid doesn't start with hydro, so therefore it means it's not a binary acid. Therefore, it means it contains a polyatomic ion. So to name acids that are not binary, we need to get our polyatomic ion chart. All right? We get our polyatomic ion chart, and we look for the polyatomic ion that corresponds to the acid here, sulfur, ick, right? And the way to name polyatomic ion acids, or what we call oxoacids, so there's binary acids and oxoacids. Oxoacids are acids that were what? What do you think?
Contain oxygen?
That's right, contain oxygen. Oxoacids are acids that contain oxygen, H2SO4, well, sulfuric acid is an example. And we can find sulfuric acid by remembering that for oxoacids, 8, if the polyatomic ion ends in 8, then the acid ends in ic. So this is the polyatomic ion. If the polyatomic ion ends in 8, then the acid ends in ic. If the polyatomic acid ends in ite, then the acid ends in us. So 8 goes to ic and ite goes to us. That's a little chant that you should say to yourself 3 times every night before you go to bed. 8 goes to ic, ite goes to us. 8 goes to ic, ite goes to us. 8 goes to ic, ite goes to us. It'll help you remember how to name your oxoacids. Okay? So the polyatomic ion, if the acid ends in ic, means the polyatomic ion has to end in 8. So sulfuric acid has to be the sulfate ion. So then we find the sulfate ion, SO4 2-, and we put on enough hydrogens, SO4 2-, right? So I put on enough hydrogens so that each hydrogen has a +1 charge so that it's neutralized. So that is sulfuric acid. Did you catch that?
That was a lot of work.
That's right, it was a lot of work. We needed to know there was an oxoacid. We needed to recognize it ends in ic, therefore its polyatomic ion ends in 8. So we see sulfuric, we find the sulfate ion, we put on enough hydrogens to make the acid. Okay, good job. Calcium acetate. All right, so we're continuing with sulfuric acid. No, sorry, calcium acetate. Calcium acetate.
Ca.
That's calcium.
Acetate ion. C2H3O2?
Very good. C2H3O2 with a minus. C2H3O2 minus. You know the charge on the calcium?
Isn't calcium +2?
Yeah, there it is. 20. It's one that has the 18 electrons, so it's going to lose 2 electrons, so it's 2+ ion. All right, so I'm going to need how many of these?
2.
C2H3O2, two of them. So C2H3O2, 2. Good job.
Magnesium phosphate. Phosphate. That's a polyatomic ion, right?
Yes, it is. So let's find that on here.
I remember. It's PO43 minus.
Okay, good. So do you remember what the magnesium is?
Magnesium, I think, is +2.
Good. You're getting there. Magnesium, 2 plus, phosphate, PO4, 3 minus.
So that's going to be 3 magnesiums and 2 phosphates.
Very good. Mg3, PO4, in parentheses 2, because this is a polyatomic ion and we want to make sure people don't get confused about what we're saying 2 of. All right, sodium sulfite.
Sulfite. Oh, there's sulfite right there. I see it. SO3 2 minus. And sodium is +1. 2 sodiums.
All right, Na2SO3, sodium sulfite. Oops, that's sulfate. Sodium sulfite, Na2SO3.
Calcium acetate.
No, I think we already did that one. We're on to number 55 now.
Oh, yeah, okay. Chlorine dioxide. Chlorine dioxide. What does that mean?
Well, it kind of gives itself away because it's saying using the prefixes mono, di, tri, that sort of thing, right? It means it's a molecular compound, right?
Oh, yeah, okay. So chlorine and oxygen.
Chlorine, oxygen.
And 2 oxygens.
Very good. Excellent. Dinitrogen tetraoxide.
N and O, 2 and 4.
Very good. Di and tetra. Potassium phosphide.
That's an ionic compound. Potassium's K. Phosphide. Is that the PO4?
You're looking at this polyatomic ion chart?
Yeah. That's phosphate. So phosphide is just the P.
That's right. Now there's phosphate, phosphite, and phosphide. So you have to kind of pay attention to that. But what kind of an ion is phosphorus going to want to form?
-3.
Very good. 1, 2, 3 electrons is what's going to gain to obtain a noble gas electron configuration. 3 minus. Potassium's a +1. It's in the first column here.
Yep. So K3P.
K3P is potassium phosphide. Good.
Silver 1 sulfide. What's that one?
Well, that's what we kind of discussed a little bit earlier, right? The silver, Ag1, is telling me that the silver has a +1 charge. All right? Because silver is here, right here, right? In that transition metal zone where there are possibility of having multiple charge states. So the silver with the +1 charge is what's, and it helped us, that 1 told us that the silver had a +1 charge.
Sulfide. Is that a polyatomic ion?
We can look at our chart and see if sulfide's a polyatomic ion.
There's sulfate and hydrogen sulfate. Isn't there one at the top, though? Well, that's just sulfide. So sulfide is just sulfur?
That's right. Sulfide is just sulfur forming a monatomic ion, not a polyatomic, monatomic. So it's S with a 2 minus charge. So I'm going to need 2 of these silver ions, aren't I?
Yeah, to balance it.
So Ag2S, that's silver 1 sulfide.
Aluminum fluoride trihydrate. What's that?
Okay, hydrates. The aluminum fluoride part should be pretty straightforward. Let's see if we can do that.
Aluminum is a +3.
Good, it's a metal. It's going to form a +3 ion because of its location.
Fluoride is a -1.
Fluoride's a -1. So we're going to want to have, we need to have 3 fluorides for every aluminum. AlF3, there's aluminum fluoride.
What's the trihydrate?
Hydrates are compounds that are hygroscopic, meaning they absorb water from their surroundings. And so when you have them in a container, let's say this is my container of aluminum fluoride, right? every time you open it, water molecules that are around in the air, and there's water molecules everywhere, they sneak down and they absorb to the surface. Can you see why that might be a problem?
Well, do they come off?
Not really well. They absorb there, they stick there. You can heat them and dehydrate them, but they'll be stuck there.
Yeah, that's a problem because then you don't have just aluminum fluoride, you have some water in there too.
That's right. Aluminum fluoride with water. And so every time you'd waste them out to perform some chemical reaction, you really don't know how much water you've got allowed to absorb on that surface because you don't know how frequently somebody has been removing that lid and so forth. Okay? Keeping chemicals dry is sometimes very important. Another way to handle that is to kind of just allow the salt to be exposed to enough water that it forms a hydrate, and then we know how much water is there every time we use it. Okay? So to write the chemical formula for a hydrate, we write aluminum fluoride, and then we write a dot and identify how many water molecules, H2O, how many water molecules there are. So this is an example of aluminum fluoride trihydrate. Okay? So the mono, tri, tetra, octa, whatever it is there to help us know how many water molecules are with this, and this is always going to be an ionic compound. It's the ionic compounds that are generally hygroscopic and that are named this way. Okay, very good. So that's aluminum fluoride trihydrate. How about silicon dioxide?
Silicon, let me find silicon. That's not a metal, so this is going to be a molecular compound. Oxygen, yeah, non-metal. So this is, yeah, so it's SiO2.
Very good, SiO2. And silicon dioxide is a compound that is like itty bitty bitty tiny pieces of glass almost. I mean, it's not like glass in terms of it's not going to get stuck in your fingers sort of thing, but it has the exact same composition, made of the exact same elements, and you find it a lot in scenarios where you want to keep something kind of from caking together, chemicals from caking together. So silicon dioxide is a compound that you find in table salt, right? The salt that we put on our food, instead of allowing it to cake together and form hard clumps that won't come out of our salt shaker, they put a little bit of silicon dioxide in there. Who knew? All right, here's some more chemical formulas.
Barium chloride,
Barium chloride. What's the chemical formula for barium?
Va, Cl2, right?
All right, so you know that barium has a +2 charge and chlorine has a -1. And so because of that, 2 plus, sorry, and Cl -1, I'm going to need 2 of these Cl -1s for every 1 barium to form a neutralized compound of barium chloride. Good. What's next?
Magnesium nitride.
Okay, magnesium. All right, we know that's a +2 ion by now.
Yep, its location on the periodic table tells us.
Nitride. Is that a polyatomic ion?
I don't think so. Let's take a look though.
All right. All we have for nitrogens is the azide. That's interesting. Nitrite and nitrate, but not nitride.
So that means it's just nitrogen.
Right.
And nitrogen forms a -3 charge.
That's right.
So is Mg3N2?
Very good. Mg3N2, magnesium nitride. And let's make sure everybody at home knows what that means.
That means 3 magnesium ions and 2 nitride ions.
Very good. So I know you know it, Fred, but just in case, a lot of people sneak by without picking up this understanding that ionic compounds are made of ions, and the reasons why they come together the way they do is based on the charges that they have. And you can't sneak by. You need to make sure you understand that, because if you don't have that fundamental understanding, then down the road it'll be very difficult to solve some problems that are given to us. All right, where are we at? Sulfur dioxide, nitrogen trichloride. Wait, what did we just do? We just did barium chloride again? what did we just do? We just did magnesium nitride. We went backwards. All right. Nitrogen trichloride. Did we already do that one? I feel like we did, but nitrogen trichloride? No, maybe we didn't. What kind of compound?
Well, because it's using tri, we know it's a molecular compound, covalent.
Very good. Dinitrogen trioxide.
N2O3.
Dinitrogen trioxide. Good. Tin, what is that thing right there? The IV.
Well, that's Roman numeral 4.
All right, so tin 4 chloride. What is that 4 telling us? Do you remember, Fred?
Where's tin at?
Tin is right here.
Is that one that can have multiple charge states?
Yeah, it can. And because it can have multiple charge states, then we use a Roman numeral to tell us which charge state we have in this scenario. So tin, Sn, that 4 tells us that it's a 4 plus charge. Chlorine, we can look on the periodic table, see where it's at, and know that it's going to have a -1. And then from that, I'm going to see that I need to have 4 chlorines. And that my chemical formula for tin 4 chloride is going to be that. Okay, good. All right, so here we're naming compounds that are metals from transition, that are from our transition metals. And if they're metals from this zone or the post-transition zone here, or even the inter-transition metals, then they have a certain characteristic. Do you remember what that is, Fred?
They have multiple possible charge states.
That's right. They can be +2, 3, 4, 5. There's a variety of different ones. Not all of them can be everything, but there's lots of different possibilities. So when we see a chemical like Cr2O3, we need to be able to name it. And chromium, again, transition metal, could be +2, +3, even +5 or +7 sometimes. Okay? So how are we going to identify what the charge is on this chromium?
Well, we know the oxygen.
And that's right. We need to take advantage of the fact that we know that the oxygen is -2 and that there's 3 of them. We knew oxygen was -2 because it's right here, right?
Yeah.
How many chromiums?
2.
We know that there's 2 chromiums. So what kind of a charge on both of these chromiums would there be to compensate for those -6, the 3 -2s or -6 from those oxygens?
+3.
That's right. So if each of these has a 3 plus, then that would balance out with the 2 minuses on the oxygens. That helps us name this as chromium +3. So we say 3 oxide. Okay?
Okay, that's the answer?
That's the answer. All right, the next one. Why don't you try this one?
Iron, it's a transition metal. There's 1, and then there's 2 chlorines.
There's 1 iron and 2 chlorines.
Chlorines on the periodic table, it's a -1. So iron must be a +2 if there's only 1 of them, right?
That's right, a 2 plus. And so this chemical's formula is going to be called, or the chemical name is going to be called iron 2 chloride. Now, why do we call it the 2?
Because there's 2 chlorides?
No, not because there's 2 chlorides. There often will be the number, but it's because of the 2 on that iron.
Oh, okay.
All right, CrO3.
Chromium's a transition metal.
Very good. So we have 1 chromium and 3 oxygens.
Oxygen's -2.
2 minus on all these oxygens.
Chromium must be a +6.
Very good. +6. 6 plus. So that 1 chromium balances those 3 oxygens.
So the name of the chemical is chromium 6 oxide?
That's right. Chromium 6 oxide. Next.
Titanium chloride.
That's right. Titanium chloride, but titanium again is a post-transition metal there. So it can have multiple charge states. So how many different titaniums are there?
Just 1 and 4 chlorines.
Okay. Chlorine,
-1.
-1 charge on all those. Titanium,
Gotta be +4.
that's right, 4 plus. So it's titanium 4 chloride. All right? Is that how you do 4?
Yeah.
Titanium 4 chloride.
Ooh, look at this one.
Yeah, that's an interesting one, right? What do you call those?
But when they have the water, that's called a hydrate, right?
That's right. How do they get that water?
They're hygroscopic. They absorb water from the atmosphere.
Very good. All right, so what is CO?
That's cobalt.
Cl, chloride, right? So what, we got 1 CO and 2 Cls?
Chloride's -1, so it's cobalt with a +2 charge. So it's cobalt 2 chloride. And then how do you name the rest?
Good. So we got cobalt 2, because there's a +2 charge there, chloride, and then we add on it at the end the hexahydrate. Cobalt 2 chloride hexahydrate.
Okay.
And then our last one here on number 57.
Molybdenum 4 sulfide.
Very good. Molybdenum 4 sulfide. So how did you know that?
Well, there's 1 molybdenum and 2 sulfurs. And each of the sulfurs has a -2 charge.
You knew that because of its location.
Yeah. So therefore molybdenum has to have a 4+ charge. And it's going to be called molybdenum 4 because of the +4 charge on the molybdenum.
Very good. All right, some more of these. With some polyatomic ions. Nice.
Nickel. I remember CO3 now. It's carbonate.
Do you remember the charge on it?
Not really, I guess.
All right, let's bring it up. Where's it at?
There it is. It's -2. So CO3 2 minus.
All right, so this compound has carbonate and a nickel, and it has 1 of each. Is that right?
Yeah. So it's going to have a +2 on the nickel.
That's right. So this is going to be called nickel 2. Nickel, is it EL or LE?
I think it's EL.
Nickel 2 carbonate. Okay, nickel 2 carbonate. What's the 2 for?
Because the 2 is the +2. Nickel's a +2 charge.
That's right. All right, what's the next one?
Molybdenum 3 oxygens, 2 minus on each oxygen. So molybdenum 6 oxide.
Very good. You're getting the hang of it. There's 3 oxygens. Each one has a 2 minus charge on it. 1 molybdenum has to have a +6 to balance that. So it's molybdenum 6 oxide. All right. What's this next one here?
That's, what's NO3? I forgot.
Let's look it up here.
Oh, nitrate. Cobalt. Each nitrate's a -1. So, is that cobalt 2 nitrate?
That's right. Cobalt 2 nitrate. There's a cobalt, and there's 2 of these nitrates according to the chemical formula. Each one has a -1, so it's going to have to be a cobalt 2 nitrate.
All right. V2O5. What's V? I don't know what V is.
It's vanadium, right here.
Okay. And then O2 or O5, 5 oxygens, 2 minus 2 each, right?
Yeah. So vanadium and where there's 2 vanadiums, sorry, and 5 oxygens. 1, 2, 3, 4, 5.
Yeah. So 2 minus each?
Very good. -2, -2, -2, -2, -2. So it's a -10. So each one of these has to be what?
5 plus.
That's right. 5 plus.
So that's vanadium 5 oxide?
Very good. Vanadium 5 oxide. All right. The next one.
I'm going to go manganese 4 oxide.
Very good. 2 oxygens. Each oxygen has a -2 charge. And there's one manganese, and it has to balance out two of those -2 charges, so it's manganese 4 oxide.
Fe2O3. Is that iron 3 oxide?
That is iron 3 oxide. Very good. All right. The following ionic compounds are found in common household products. Write the chemicals for each of them. Potassium phosphate. Can you write the chemical formula for potassium phosphate?
Oh, there's potassium K, phosphate ion. Is that, can you look at that for me?
Sure.
PO4 3 minus.
Very good. PO4 3 minus.
Potassium's +1, so it's K3PO4.
Very good. There's a chemical called TSP, trisodium phosphate. TKP, TPP, tripotassium phosphate, has the same properties. It's pretty good at pulling paint off the walls. You put a little bit of water on it and rub it on the wall, and it will pull the paint off pretty good. It's kind of a strong base. We'll talk about that in the future. Copper 2 sulfate. Chemical formula for copper 2 sulfate.
Sulfate. I think I remember that's the SO4 2 minus.
That's right. Here it is down here. SO4 2 minus.
And there's 1 for every copper. Or no, what's the copper 2 again?
The 2. What is the 2 telling us?
Oh, that's the charge on the copper ion.
That's right. +2 there.
So it's just CuSO4.
That's right. CuSO4. That's our copper sulfate.
Okay, calcium chloride,
Calcium chloride.
Ca and Cl, CaCl2.
Very good. CaCl2. That's calcium chloride. Calcium ion and chloride ion, we know their charge states simply by where they're at on the periodic table because they are representative elements.
Titanium 4 oxide, titanium 4. What does that 4 mean again?
Think about it. Titanium and oxygen coming together to form titanium oxide of some sort. Titanium 4 oxide.
The 4 is telling us the charge on the titanium because titanium is element 81, which is a post-transition metal.
Very good. So it could have multiple charge states, right?
So here it has a 4 plus.
All right, the 4 tells us that. Oxygen has a 2 minus always because of its location. So this is going to be Ti what?
O2.
Very good. TiO2. All right. Ammonium nitrate. Ammonium nitrate.
Those are both polyatomic ions. I remember them now, though. I'm getting better at the polyatomic ions.
What's the ammonium ion?
NH4 plus,
Very good. NH4 plus. What's the nitrate ion?
NO3 minus.
Very good. NO3 minus. Nitrate. Ammonium nitrate. So it's 1-to-1 ratio. Is that it?
Yep, NH4 NO3.
Very good. Ammonium nitrate. All right. Sodium bisulfate. Common name for sodium hydrogen sulfate. Sodium hydrogen sulfate.
Sodium, Na. Hydrogen sulfate, HSO4.
Very good. And you knew that it was a 1-to-1 ratio because the hydrogen sulfate has a 1 and the sodium has a 1. We've worked with that one a lot. Location on the periodic table, right?
Yeah.
Okay, on to number 60 there. All right. Following ionic compounds are common household products. Let's name them.
CaH2PO4. What is that?
We don't have the tools to name that compound effectively. Well, yeah, I guess we got it okay. H2PO4 is our hydrogen phosphate, no, sorry, dihydrogen phosphate ion. So calcium, Ca is a 2 plus. H2PO4 is a single minus. And therefore, I'm going to need to have, oh, well, I just need to name it. Calcium dihydrogen phosphate, right?
Yeah, okay, sounds good.
FeSO4, what do you think?
Iron and SO4. Is that sulfate?
Let's double check here. Yeah, there's sulfate.
Iron sulfate.
All right. Iron sulfate. There's something wrong with that name. Do you know? Can you catch it?
Is it sulfite?
No. Where's iron at?
Oh, it's a transition metal.
So what does that mean you have to do?
We have to indicate the charge on it.
All right. Can we tell what the charge on it?
No, we can't.
Well, we can. There's some way.
Well, how?
We know the charge on the sulfate, right? We know it's a -2, right? SO4 2-. And iron must be something that's such that there's 1 to 1. Is that what it says? 1 iron? Where are we at? Right there. 1 iron for every sulfate, right? Okay. So that means that this has to be a 2+ as well. So the name of the compound is actually iron 2 sulfate. Good. CaCO3, letter C.
Is that calcium carbonate?
Very good. CaCO3, calcium carbonate. MgO,
Magnesium oxide.
NaNO2,
NO2. What's NO2? Oh, it's nitrite. Sodium nitrite?
very good. Ki,
Potassium iodide.
very good. All right, some more names. Magnesium dioxide. Magnesium dioxide. Oh, it's not magnesium dioxide, it's manganese.
Yeah, manganese.
Okay, so manganese dioxide.
MnO2.
All right, so manganese, MnO2. That's not the right name. MnO2 isn't. We wouldn't call it di, would we? Why wouldn't we say use the prefix di here?
Because this is a ionic compound, not a molecular.
Very good. So what should it be called?
Manganese oxide. Just manganese. Well, no. Oh, is manganese a transition metal?
Let's look and see here.
Yeah, it is. So we need to give it a number. Oxygen, there's 2 oxygens. Each are a 2-. 1 manganese. So it's a +4?
That's right. So manganese 4 oxide is the appropriate name for manganese dioxide. Manganese dioxide is not the right name. Okay. Mercurous chloride used to be the way we would call it. There's a better name for it now.
I don't know what's going on there. Why is there 2 Hg2Cl2?
Yeah, this is kind of a squirrely one, and we're not going to hold you to knowing the name for this one. But let me go over it here for you. The mercury ion can either come as a Hg plus or an Hg2 with a +2 charge. Kind of interesting, kind of molecular in nature. You'll notice that there's lots of exceptions all over the board when it comes to chemistry, and this is one of them. But the name of mercury Hg2Cl2, 2 Cls, and one of these Hg2 with a +2, this is called mercury 1 chloride because the charge on each of these mercuries is 1. Even though there's 2 and together they have a +2 charge, each one has a 1. So mercury 1 chloride would be the correct name. All right, titanium tetrachloride. All right, titanium tetrachloride. It looks like they're meaning this, right? Now, why shouldn't that be called titanium tetrachloride?
Because titanium's a metal, it should be named following the ionic compound.
That's right. So titanium has to have what kind of a charge in this scenario?
A +4 charge.
That's right. Good. There's 4 chloride ions, and therefore there has to be a 4+ charge on each titanium.
So titanium 4 chloride is better?
That's right. Titanium 4 chloride. All right, cupric bromide, another old way that they used to name this compound,
CuBr2.
CuBr2.
Copper 2 bromide,
Very good. Copper, how did you know it had to have a +2 charge?
because the bromide ion has a -1.
Right. And there's 2 bromide ions, so it's a 2+ charge. So copper 2 bromide is our right name. We did it, Fred. We did it. Good job.
That was a lot to name.
Yep. But a lot of learning too. Good job.